Today we're working on more conservation of energy problems, but I promise you today is going to be a lot easier. I'm going to show you the simplified way to do it, and then we're going to do work energy theorem as well, in case you forgot what the work energy theorem is. So if you previously printed the notes, I updated them. They look a little bit different now. We have the work energy theorem on the top, and then we have some conservation of energy formulas at the bottom. So sorry about that. All right, let's get started. So in case you forgot, the work energy theorem just states that the work, well, the net work, is equal to a change in kinetic energy. A change in kinetic energy is the same thing as saying KE final minus KE initial. And then we know the formulas for KE. Don't forget, you do know those. KE is just equal to 1/2 mv squared. We don't always have to have an initial kinetic energy. Sometimes an object's starting at rest. If it's starting at rest, then there's no need for this. So work can just be KE. Like in example 1, that's what it's going to end up being. So in example 1, we have a 20 Newton box. Newton's measures force. It sits 5 meters high on a ramp. 5 meters measures our distance or our height, whichever one you want to use. What is the kinetic energy at the bottom if the box slides down? So we're looking for our kinetic energy. So on this one, we're given force and we're given a distance. We know that with force and distance, we can find work. So we're going to use our work equals a change in kinetic energy formula. Just think about the scenario. A box sits on a ramp. If it's sitting, does it have kinetic energy? No. So there's no initial kinetic energy. And that's what I'm saying. This formula is pretty easy because most of the time there's no initial kinetic energy. So we're just going to use the formula for work being force times distance equals the formula for kinetic energy, which is 1/2 mv squared. And that's all we have to do to solve this problem. So our force is 20. It's sitting 5 meters high. 1/2 is the same thing as saying 0.5. My mass, we don't have mass. Oh, but it's not saying for kinetic energy. We don't need to solve for velocity. Sorry, we're just solving for KE. I'm making this way too complicated. All we have to do is multiply 20 and 5. Sorry, guys. 20 times 5 is 100. I made that way too hard, didn't I? Yes, I did. Sorry. Pretty easy though, right? Okay. Let's move on. So I showed you the long formula for conservation of energy yesterday. I'm going to write it out again. And then y'all are going to hate me for this. But I have to show you the hard stuff before we can get to the easy stuff, right? All right, so according to the rules of algebra, if you have the same variable in each, basically parentheses, in each mini formula, you can totally erase that variable and still get the same answer. So look at all of these formulas. What is the same in each parentheses? What do you see in every single parentheses there?
Mass.
Mass. So you can solve this formula without using any mass. But this only applies if the mass stays the same, which most of the time it does, right? If a ball's rolling on a ramp, it's the same ball the whole time on the ramp. If a car is going up a hill, it's the same car going up the hill. So mass doesn't change. So this formula can simplify down to 1/2 v squared plus gravity times height equals 1/2 v squared final plus gravity times height.
Shavina, why didn't we do this yesterday?
I told you it'd be easier today. I have to show you the hard stuff before you can get to the easy stuff. It's like teaching you math before I give you a calculator, you know? Didn't you do that in school? First you use math without a calculator?
No, we went straight to calculators.
No, you did not. All right, so let's go on. Again, today's going to be a lot easier. We got rid of all the hard stuff, so it's going to be easy. Don't worry. A 5-kilogram ball is thrown vertically upward. Well, kilograms are mass. With an initial KE of 20 joules. How high will the ball rise? All right, so this is an even more simplified version than the formula we have, because we know 1/2 mv squared is KE, right? It's thrown upward. So do we have an initial height? No, we shouldn't have an initial height. So technically, it's this formula just without this. And if the ball's going high as it can go, what's the velocity at the very top? Always.
0.
0. So are we going to have a final kinetic energy?
No.
No. So technically, this is just our formula. 1/2 v squared equals GH. But we know already what 1/2 v squared is because it told us what kinetic energy is. So don't write this down. I'm just going to show you what the formula is and what we're taking out. So KE initial plus GPE initial equals KE final plus GPE final. It told us what our KE is, so that's 20. Hello, we don't have an initial height. There's no initial height. So we don't need that, so that was plus 0. Again, we're at the top. No KE at the top because there's no velocity. If there's no velocity at the top, there's no kinetic energy at the top. And then we have our formula for mass, gravity, height. You get what I'm saying? Does this not make sense to anybody?
It's a little bit. I got confused towards the part whenever you like started taking out the first GPE and KE.
Well, you can write it the long way if you want and just plug in zeros.
Oh, did you add the 0 because like the information isn't there?
I added the 0 because height would be 0 at the bottom when you're throwing it up.
Oh, okay. Yeah, that makes sense.
And then I added the 0 because your velocity at the top for kinetic energy would be 0.
Okay. Yeah.
Most of the time, honestly, these are going to be scenarios where kinetic energy initial is going to equal potential energy final, or gravitational potential energy, and vice versa. Gravitational potential energy initial is going to equal kinetic energy final, because we're going to be talking about objects either going up or objects going down. So in this formula, we knew our kinetic energy. We didn't have to solve for it. It was just 20. Our mass was 0.5. Our gravity is 9.8. And we're solving for H. Do you know what to do now?
Yeah, you multiplied the 0.5 and the 9.8, and then like the h is attached to that, so then you're divided by the 20.
Yes, perfect. So you should get your height to be 4.1 meters. And today, honestly, it's going to be easy. Probably the last example I'm giving you today is going to be the hardest problem you're going to have. Are we ready to go on to number 3? Are there any questions for number 2? All right, let's keep going. A ball is dropped 10 meters above the ground, so we know that's our height. How fast is it traveling right before impact? So we're looking for our velocity. Same thing going on here. We know it's dropped from a height of 10 meters, so is that our initial height or our final height?
Our initial.
That's going to be our initial height. We want to know how fast it's traveling right before impact. Is that going to be our initial or our final velocity?
Final.
Final, good job. All right, so we're dropping a ball from the ground, above the ground. How fast is it going at the beginning?
0.
0. So there's no initial velocity. Velocity initial equals 0. And if it's going to the ground, what's the final height going to be?
0.
So height final is 0. All right, so we got a lot of zeros. We could get rid of a lot of stuff from our formula, right? Let's write out that formula again. KE initial plus GPE initial equals KE final plus GPE final. If our initial velocity is 0, what can we get rid of?
The first KE.
The first KE. If the final height is 0, what can we get rid of?
The
final
second GPA.
GPE.
The final GPE. So there we go. We just simplified our formula. And what did I say to do about your masses? Just
You can take them out.
So really our formula is gravity times height equals 1/2 v squared. Isn't that lovely? Much easier to solve now, right? All right, so now you can plug in your numbers. Gravity is 9.8. Our initial height was 10 meters. We still have our 1/2. And we're looking for our velocity squared. Using rules of algebra, you multiply 9.8 and 10 first. That's going to give you 98. And then what do you do with that 98?
Divided by 0.5.
Yep. So that's going to carry on to 196. I don't know why I put a decimal. Equals v squared. And what's the last thing you need to do?
Square root it.
Square root it. So your final velocity should be 14 meters per second. How easy is that? Don't you just love today? I told you it'd be better. Any questions on this one? All right, let's keep going. On a loop, a ball is going 5 meters per second at its lowest point. How high can the ball reach on its highest point? All right, so we only know one thing on this problem. We know the ball is going 5 meters per second at its lowest point. We want to know how high it can go on its highest point. All right, so let's go over some things. It's going 5 meters per second at its lowest point. How high can it go on its highest point? Is that 5 meters per second going to be our initial or our final?
It's our initial.
Initial, good job. That's going to be our initial. If it has the lowest point, what does that tell you our initial height is going to be?
0.
.iHeartMedia.
0. Height initial is going to be 0. So that means what height are we looking for?
Final.
Final. We're looking for our final. And if it's at the highest point again, what do we know about velocity at the highest point before it comes back down?
It's 0.
0.
0. So our final velocity is going to be 0. So let's write out our formula. KE initial plus GPE initial equals KE final plus GPE final. All right, let's knock some things out that we don't need. If our if our velocity initial, if our height initial 0, what else is going to be 0?
The GPE initial.
GPE initial, we could cross that out. If our final velocity is 0, what else is going to be 0?
Our kinetic energy final.
KE final. And don't forget what I said about knocking out those masses. You don't need them anymore. You didn't really need them to begin with, but ha ha ha. So you have 1/2 v squared is equal to mass, I included the mass, gravity times height. Then you just plug in your numbers. 1/2 is the same thing as saying 0.5. We know our v squared, that's 5 squared. Don't forget to square that. Gravity is always 9.8. We know that. And we're looking for our height. Rules of algebra, what's the first thing you need to do?
Multiply the 0.5 with 5.
Squared, right?
Sorry.
Don't forget to square that 5.
So that's going to be 25 times 0.5.
Huh? So you should get 12.5 equals 9.8 H. What do you do next?
Divide.
Divide.
98 by 12.5. I mean 9.8. I said that wrong too.
Me too. Sorry, I messed you up. So 12.5 divided by 9.8. Your height is going to be 1.28 if you round it. Easy peasy, right? We're good. Does it all make sense now? Isn't it all easier? Now you're going to fly by this fast. All right, now this last one, you're going to hate me, but I promise you if you pay attention now, you will thank me later. A 1 kilogram object is thrown vertically with an initial velocity of 15 meters per second from the top of a building 35 meters high. All right, so let me draw that for you. You're standing at the top of a building. You're throwing a ball up. How do you know it's throwing up? Because it's a positive velocity. If it's a negative velocity, which way am I going?
Down.
Down. But since it's positive, there's no negative, I'm going up. So it's going up. On the way down, it just missed the edge of the building and strikes the ground. So instead of it coming back down to where the guy's at, it goes all the way down to the floor. My picture's not drawn to scale, but do you kind of get what's going on in this scenario? All right, how high above the ground does the object reach? So this is why I wanted to draw it out for you, because it kind of confused me when I read it. So I wanted to draw it out so I could visually see what was going on. So from this point, I'm 35 meters. I want to find out the height from this point. That's what I'm looking for, that height. Yeah, that's all I needed to draw. Now we can find out everything we need to find out. 1 kilogram object is a mass, but honestly, do we even need masses anymore? Sometimes you will. I take that back. Sometimes you'll need your mass. So let's not forget about it. We also know the initial velocity, so that's my VI. We know our height is 35 meters high. And we want to know how high above the ground it does reach. So we're looking for a height. So we have two heights. You just have to figure out which one's the initial, which one's the final. And I'm just going to tell you, if you're throwing it up from 35, that's your initial height. And then we want to know how high it's coming back down, so that's going to be our final height. One more thing, it strikes the ground. So what do we know about the final velocity?
It's 0.
Final velocity is 0. All right, so let's write out our formula. Keep using red today. KE initial plus gravitational potential energy initial equals KE final plus gravitational potential energy final. We only have 1 0 in this problem, so what's the only thing we can get rid of?
The KE final.
KE final, that's the only thing we can get rid of, unfortunately. But like I said, we don't need to have our masses, so 1/2 v squared plus gravity times height equals gravity times height final. Now we're just going to plug in our numbers. 1/2, I like using 0.5. V squared, that's 15 squared. Plus gravity is always 9.8. Plus our initial height was 35. And that's going to equal gravity again, 9.8. Times my height, which is what I'm looking for. So rules of algebra, remember you can't add first, you have to multiply first. So first we're going to do 0.5 times 15 squared. That's 112.5 plus 9.8 times 35. 343 equals 9.8H. Now you can add 343 to 112.5. That gives you 455.5 equals 9.8H. And what's the very last thing you need to do?
Divide.
Divide.
You have 40.48 if you round it.
Say it again.
You divide in it, that gives you 46.48 if you round it.
Good job. 46.48 meters. Sorry, I forgot meters. Honestly, on today's assignment, this is the hardest one you have to do. And if you're paying attention, I just told you how to find the answers. That's pretty much it. Good luck. I'm going to stay on Zoom the whole time if you need my help. If not, you are free to go.